that centennial volume series of Bureau, and which is variably getting done.
People are available to do that.
John Medish had good intentions. People didn't follow through.
Could you tell me when I get on the camera?
Yeah, you want
Oh, you're good.
Good? In the camera still?
No, not really.
Okay.
He made the distinction.
So,
I think a lot of pushing from Colleen Elliott and a few others within the Bureau that they should just make this
Yeah.
online item
Water,
and
citric acid,
extend,
sodium,
the time period in which these documents come in.
flavors, aspartame.
The problem with that is, of course, it really gave out to a number of people. So, right. So, I'm on another paper on the Cambrian, and my co-author, who I won't mention his name, just
soda can, or two soda now, because the movie caught up on
my draft, and off it went into the black hole. And that individual kept talking to me, well, I got a big field season this season. As soon as that's over, I'll be there, et cetera, et cetera. And, I just figured I'd like to get that done.
Or no, what?
The Cambrian is extremely interesting in Montana. And I've got a lot of stuff I went in there, get out in that summary, paper that is not particularly good for, lithosphere or geology or some of the publications.
So you guys got your pass on the way
I
out to like.
backed off of some of that stuff.
Yeah, we went to talk to the dump.
Yeah.
Well, not to the dump, we went to the, what was that site?
And I haven't done tobacco for quite some
I was
time
waiting
because
pass
I edited for years, edited for years, and it was like, okay, once the book started with Yellowstone, not continuing to do TRGS. I'll go back to TRGS soon. I'm gonna go this
No, so
summer.
Didn't they work on the anaconda again last year?
They went to Comanche. And it was apparently just absolutely terrible.
Ooh,
10
I like that
plus.
one actually.
And,
Cause like basically you get tested.
I think it was really likely.
Exactly, it's like you don't have to really try very hard.
I didn't know when to go when I saw
Yeah.
what the weather was. It was like, oh, so I don't know what, this coming one is a belt association combined. And because Don Winston passed away in
Winter, he would show
the
up
summer,
with no shoes, no socks.
last year.
Just gets out of the shower.
But
I
actually,
fully
you don't
expect
like the
that
shower, it's
there's
actually,
gonna be a fairly big gathering.
It's just the shoes like.
And
a lot of
a fair
events.
amount of dedication to this trip.
And I was looking from across the room.
It's still gonna
Like,
be working.
Yeah,
What's the plan gonna be, the Beltwood parking lots
In
in
that class,
Idaho, anyway, in the salmon area, trips, things like that.
I don't think she worked there anymore.
In any case,
Yeah.
the tobacco area is a really great society.
Yeah.
It's a place where a lot of things like this didn't get published, that, in field data can be published, it can't be published pretty much anywhere else. I've often said that I thought it was the best grade literature, anywhere in the country. That's true.
Because she was actually
Really great resource
I was,
that
that
just
was
came
awkward. I told her my
They published in
Yes, I'm
Or his lectures.
Everybody.
People goes down that.
Right.
So there's a lot of.
You ready?
5,
Oh,
I
yeah.
can't read that. 504,
This makes a
509.
great way under the back road.
Or 5.0.
Yeah.
Your line.
Yeah, we,
No, that's the time.
when I
Oh,
was,
that's a good time. Oh my
when
gosh.
I was the president,
Oh my gosh.
Dick Gibson and I worked together. Dick founded
The government, anyway. I was like, oh my God, why is it going? And I go, why is it going up so fast?
Post field camp.
It's like.
Let's drink beer and go back to the Tobacco Root Mountains, gathering with his friends. And do some field trips. Langston, he's out in Missoula. And so they did this and they
Yeah, exactly.
turned this thing into this annual event. They just decided we had so much fun, let's just keep doing it. Then other people started tagging along. And they started publishing road guides in the handout that they had made.
And then they're like, oh, what are you doing? Because I got you. I said, no.
They arrange,
You
you know,
know,
private property.
It's probably,
There's a whole stack of them.
yeah, that's good.
We had two
Those changed over time.
No, I brought 2. And I was.
Yeah, never mind.
Hi.
Hey,
No, like 2, like.
Current owners aren't, so.
have some pizza.
Not that it's 2, like, hidden
There's a
valley.
ton.
They do 2 big stuff. Yeah. Oh, big stuff. I had for the first time.
Happy.
I was spending that Irish in Idaho, and I was like, ooh, let me try.
Yeah.
big stuff.
Yeah, I don't know.
Big stuff.
So anyway,
High quality.
So we've been
Northwest
Also,
Geology
the
was,
I tried came for the first time.
as I
Their
understand
chicken,
the rumor,
not really good, like you like flavor.
from Sheila Roberts,
But it's because.
was started by Dave Holtz as a non-peer reviewed place. He gave that's why he started roadside geology.
Yeah, we're up to 700 and 400.
It was a long story. Why
There's
he made it peer reviewed. He started it, and it was just a place to
Oh, yeah.
provide geology in the Northwest, mostly.
That's right.
And it wasn't covered, tobacco in that way. And then tobacco was just used and published in Northwest Geology. And then Northwest Geology then publications a year, depending on what was going on in the geology world. And one of them would be
Hey, Kevin.
field
Wendy?
guide. So, yeah, Gibson, when I took over, we have to have a journal.
Hell's going down in the south.
And I said, I don't think anybody at this point cared if we just stole Northwest Geology.
I could tell you.
And made it ours. I said, I will talk
I
to
should
you.
kill
Make
it.
sure that.
I think this was for like,
Yes,
you did. This is what, like.
Good.
It'll be just a efficient journal.
Yes, I, extra time.
So Northwest Geology will forever be the publication of the Geological Society. That really was strong and never died.
I think that's like
The
ours.
Tobacco Geological Society never died.
You can read.
Because this pub has to be put out every year.
I know, exactly. Yeah. Not bad. It's good that it's busy since we published.
One that's got in place, publish it, and it's now peer reviewed and it's edited, but it's really, the amount of peer reviews limited. You can't afford giving the time frame, to send it out. Robust, I could imagine. What we do is we ask one person, right, who had experience in that area, because you just read the transcripts. we have an editor, don't worry about that. Just let us know, contact, is that okay? It's bonus, tell us if it's okay, tell us in the college. That level, but you're okay. And the goal was to not see what happens.
Yeah, we'll see.
We'll try to protect what turf and acts out paper. Like traditional.
Exactly, that's what I'm saying.
That happened. That's what happened to Dave Ball. That's why he didn't want to stay. So, dogs, we're in tobacco is in a great situation. They have lots of them. What they really need are the continuance of
But it's
so
3 weeks, like you gotta go to Kalispell to the states of that country where it's been.
so it's almost like, I mean, when I came in, the people that, sucked me in is the new guy.
13, 14,
Yeah.
15, 14, 15, 16 of April.
Yeah.
It's all for her. Have woods.
I know it's stuck around for a while.
We've had a new camper, well, like new to us.
That one mark coming
The people that, we did actually live in the state in Little Decent, which is, you looked at it, about that was around, everything. That was they swear by God's word. And I
got a new guy.
No, we tried it.
Somebody who's connected.
We didn't leave it set up overnight or anything like that. No, it's decent.
Outreach guy.
Yeah. And then you don't have to, you don't have to worry about asphyxiating yourself. Because it's actually, the unit is outside and air intake and straight fresh air. Mother Nature.
I don't know if he's your kid's possession.
No, I'm still pretty gross, man.
I know what you're fiddling with it. Hot air.
I went in the back.
Right up a little bit. You could feel it on your feet, right? 2 minutes.
Right.
Let's probably get my
Yeah, I think that Euro is like Welsh combination.
And it should be 30 below in Kalispell.
Or with the higher. It's
Keep our fingers crossed.
So
No, I know that if it is
very
that
small
cold,
retired.
we won't be able to do
Engineering. Yeah. Skiing. I know. Yeah, he was right. Yeah, he did. So, memories. So they've got Celine from who used to teach for us. Just 101 classes. She's doing her PhD. They got her as a PhD student. I think they got something. I'm not
Already,
it's
overflow and maybe got 2
yeah, Chris is 67. So Chris will do your 7th Street. And very good. Oh, yeah. I mean, he's one of the teachers that just decided to hold on. It's hard to do. I will say, yeah, I mean, they're not gonna leave.
Okay, yeah.
It's just a matter of when he decides, you know, time spent fly fishing on the big holes more important. It's time to go teaching.
That was like greatest publication.
Oh, he's the funny guy. Yeah. But he was born rich. No, absolutely. No, he's absolutely. We have oh, yeah. He was scared of living daylights like students. Yeah. You know, because he's huge. Yeah. He's intimidating until you realize, you know, this is the nicest guy around. You know? And you're right, I mean, you have to nail him in the head. He's this crouching persona that is nothing actually like that.
To the point.
Oh, Chris is great. I've known Chris now for 30 years. And, had a lot of collaborative interaction with him. And they've been lucky to have him. And when he retires, it's going to be rough.
Really? When he retires, nobody will run the XRF.
Yeah. There's no, there may not be anybody around that can run XRF, you know, anymore. I mean, it's getting to be a tool that is not commonly used. Yeah, I know.
So did he ever?
I mean, there are exclusive uses to the XRF, there's no question. But microprobes and, you know, other kinds of analyses. Oh yeah, there's so many tools. The XRF is kind of, I think of the XRF as
So
honestly.
when you're out wandering around in the middle of nowhere and you've got.
They're almost.
Well, that looks like it could be.
Oh, not the XRF for lessons. Yeah, I was XRT is what I was thinking about. Yeah. No, his XRF now is great. It's wonderful for getting you know, kind of low end data, right? In the field, quick shot on what you've got on the sample. We've used it a lot actually.
I see something over here, what is that?
Yeah, no. Yeah, the consulting firms all use it, right? They use that. Yeah, I was thinking XRD. So X-ray diffraction, that was the state of the art machine 40 years ago.
You take a sample and you take it to the lab, you prep it and you put it in the machine.
It just doesn't, it provides peaks, right? So it's a mineralogical tool. It provides peaks, and you have to know how to read peaks.
Yeah, what wavelength?
Right, that's right. And it's very cumbersome machinery. The prep is awful. It's great for plays. That's what it's best for. Clay mineralogists still use XRD. But you get the same data out of the microscope.
And the only thing
And you can get quantities.
sad is the top of node
So,
So neat because you can just. Portable.
but that thing's great. Yeah, that thing's great. I really wish that we could afford one. They're about 50 grand.
I think they told us when he first brought that one out, 40.
Yeah.
That's why he keeps it in that case and carries it.
Yeah.
Nobody gets.
Sorry. I need help. I'm
It's,
going,
it's,
down my last minute. Sorry.
it's a tool that we really need. And,
Sorry.
you know, when our geophysicist came on, we wanted to get him, you know, pushing out at getting
somebody hopefully
so putting our eggs in that basket, bought himself started. electrical resistivity device, which is his tool of choice. He's going to be buying a ground penetrating radar device for next year. Equipment budget.
Oh, well.
And that's not a real cheap item either.
You have
Incredible usefulness. You can do anything from archaeological work to, using it to find buried pipes in the city. Although no one needs that because all you do is drive and you can find out where the buried pipes are.
Who's going to buy the drone and the LiDAR?
We bought a drone. LiDAR, we don't yet have. But we do have a drone. And we have everybody licensed to LiDAR.
The drone is capable of all that LiDAR.
I suppose it is.
Not so heavy.
It's not a toy. We bought a good one. True. They're all toys. But we bought one that can handle a very large camera. Because we want to be able to use it for tracking sedimentary structures and streams, variety of items. Yeah. I haven't used it yet. Spruce Shunman has been the primary user thus far. But I certainly could have used it in field studies class on rivers. It's a great way to fly over and see what well, first of all, you can document from the air, change over time. So whoever replaces me can use that, to continue to do stream work and document change over time, which is great.
The source higher.
No.
I got thinking the other day, we built, they call it level all the way up to the ballasted down whole piece of track.
You gotta work with someone with smokestack, mineral, yellow, or
or somebody cleaning up.
Yeah,
that's right.
That's the stuff that is chemically reactive.
Right.
But I'll look. Maybe I have.
Even the sighting, for.
So like the color.
Yeah, kind of greenish, yellow.
Okay, I'll look for it. I think I've seen particles like that. I mean, I've seen slag, but the slag, most from the
Yeah, there's a lot that goes into this.
So,
They want to build windmills on
the
the
vast majority
and they
of
got all the way up
settlement
until the last process.
Geological Valley is directly
And the government said, well, we can't build this in, can we find fire?
because we're building slag.
They didn't want to disrupt the flight.
Right, but what you're talking about is chemical problems today, right? And are they coming to be at that source?
But if
Because
you're a landowner,
you shouldn't be everything at once.
just retire after they get their windmills.
And yet, we know from a lot of people, that's not the case. And I'm talking short slag.
Really only.
Yeah. Right.
There's a hot spring there.
Right.
Limestone, somebody poured into the hillside right there. Holy stuff was making down below. All those tracks. Carrots, downgrades, great, of course.
It is a good school.
We lived there with kids.
Yeah, sure, sure. Okay, we better do this. So anybody, last chance to grab a piece of pizza? And I'm gonna have our student center, learning center guy set us going, because I told people in cyber world we'd start at 4. So we're ready to roll on that? Okay.
Oh, yeah. So they need a consultant.
Tom?
I actually signed up. That's how I do it.
Read where the camera will pick you up.
One thing,
So the range of movement where the camera will stand just to this side of the screen and still be in the camera. Yeah, any further out you'll be able to. Yep, thanks. Yep.
I'll pass some of these around. Okay, I think we'll go ahead and get the show on the road. For those who don't have a copy of the geological history of the Dillon area, this is a book that students put together a while back. A lot of you have it already. I know. But I thought I would pass this around because this talk today is covered in the booklet. So pages 15, 16, and 17 are there. So take as many as you'd like. I've got a ton.
so do I.
Which does not reflect whatsoever interest. Just reflects the amount of money that the foundation put in printing. Okay, well,
I've got 2 copies at home.
this talk was so exciting that all of my colleagues in the environmental sciences department left town. So there's no one to introduce me. So I'll introduce myself. This has got to be a first that this has happened. When do you do it? I won't put you on the spot. I don't dare let Jack do it. So I'm the Matchbox 20 guy. No, I've been here, as I like to say, since God was a child. And Jack was here before me, so what does that make you, Jack? 3 gone. And actually On the Rocks I created On the Rocks to have a science speaker series when we were all together in one department of science back in the day. And so it's great to be able to talk about a project that also goes back to that time period and continues to this day, about the headwaters of the Upper Missouri and how it developed. When I first arrived in the Dillon area as a faculty member, I was already aware of an initial project in the late 1980s that was being done by Jim Sears, who was Johnny's advisor at the University of Montana in Missoula, and Bill Fritz, who was at Georgia State University and a graduate of U of M, and who I co-authored Roadside of Yellowstone Country with at a much later date. And the 2 of them were teaching field camp with the myriad of other field camps that are in Southwest Montana each summer. And they were doing a project out on the Sweetwater Road east of town called Timber Hill. And Timber Hill had been mapped for decades prior to that, just as a mapping project. And nobody seemed to recognize the importance of it till probably Jim Sears. I'm not going to give the credit to Bill because Jim is brighter than the average and likely the guy that realized what he was looking at. So out there are a bunch of gravels and sands, and they're rounded. So what do you think of when you see a rounded cobble? Streams, right? So you immediately look at these and you're like, oh, these are stream deposits. And they're interbedded with ashes, and the ashes have these big, huge cross beds, and the cross beds are really clear, to even an entry-level geology student. That looks like that's been transported by water, right? So that looks like a stream, and then capping the whole thing is a flow of basalt. And the basalt can be traced physically all the way back to just south of Lima. And then poking around, they found the vent that this flow came out of, and it's in Idaho. And all of a sudden it dawned on them, we do not understand at all the timing of the formation of the mountains in southwest Montana. Because when I was a student, as a grad student in Missoula, the thinking is that the mountains and the valleys that you look at today have been just exactly as they are for about 50 million years or so. Now we know that the black-tailed deer range, which you can see from campus, popped up in the last 4.5 million years, max. The centennial, only about 2.5 million years. Okay, that now gets my attention because that's scary from a earthquake hazard standpoint, that the topography is that tremendous over that short a period of time. You can calculate the uplift rates by looking at connective tissue across the range to the valley, right? And figure out how much it's been offset over how much time, and you can get a rate of uplift. And that rate ranks about third highest in the world. Behind what? Anybody know? What's the fastest up? Right, the Himalaya, right? Okay, why is this happening? Well, the world's largest explosive volcanic center is to the southeast of this area, Yellowstone. And so I'm going to put all this together for you so that you can see how it is that these mountains have formed over time, how the valleys have formed over time, how they have changed the flow path of the Missouri River, and how it relates to Yellowstone, and how the deposits that we find from the ancestral Missouri River allow us to reconstruct that hotspot and how it functions. Most people want to study the calderas themselves, the volcano itself, right? But you can learn a ton by what comes out of the volcano and flows down the river valleys and is not anywhere close to the caldera, the volcanic center itself. Make sense? Okay. So with that, we will visit if this thing's going to work.
I saw it once.
Yeah, it did work once, but okay, that's all right. I'll use my finger. Okay, so there we go. So when you look at a topographic map of the headwaters of the Missouri, probably just at first glance, you don't see any pattern, right? But I see patterns all over the place because I've been looking at this for 30 years. And I understand those patterns now. So I'm going to teach you why it has that pattern. All right. So let me point out some of the patterns. It's just not going to work. There it is. No, it doesn't work on the screen. Whiteboards don't allow. See? It just won't show up. It's just barely there.
Totally up
See
to
it really well?
We can see that.
Can you see it?
Oh, yeah.
It's me because I'm looking at it at an edge.
I can't see it, but we can.
Okay, I'm gonna use my finger.
Just don't touch it.
I was born with that. Okay, so one of the things that you guys tell me. So using north as your compass, what pattern do you see of valleys and mountains? What direction do you see a pattern? What, Jack?
Well, there's a lot of north-south, but except for the centennial.
Not really truly north-south though, right?
Northeast.
Okay, let's start there.
Northeast.
So let's start with okay, we'll go to the northeast. So there's a segment of Northeast River there on the Big Hole, right? There's the Beaverhead Jefferson northeast until it gets right here. Then whoosh, look at that jog through the canyon of the Jefferson, right? That gets my attention. And then northwest trend to the Madison here, and then northeast to the Three Forks. See it? All right. The other major pattern here is northwest.
Right.
All right. We can all go all the way down here to Idaho. Range, valley, the continental divide, range, valley, range, valley, range, valley, range, valley. Okay. So there's the Tendoy Range right there. There's Clark Canyon Reservoir and the Red Rock River. There's Mission Hills. There's the Blacktail. There's the Blacktail Valley. There's the Sweetwater Range. There's the Sweetwater Valley. There's the northern tip of the Ruby. There's the Ruby Valley. There's the Tobacco Roots. See the trend?
Absolutely.
Okay, absolutely.
Now that's the early ones.
I'm not going to tell you that yet.
Okay.
Because we could just eat pizza and go home. All right. So there's two clear orientations to the topography in Southwest Montana. There's a northeast trend and there's a northwest trend. Okay? And then there's some weirdos like this path here across the northern tip of the Pioneer Mountains where the Big Hole goes. And notice that its orientation looks suspiciously like the orientation of the canyon of the Jefferson. Got it? Southeast. Got it? Southeast. And cutting across mountains. Rivers don't do that. Right? They don't bore holes. They've got to be set down on uplifting topography to do that. Okay, just keep that in mind. Okay, so to really explain this whole story, we're going to go all the way back to the time of dinosaurs and before there ever was an upper Missouri River. So let's go back to the Cretaceous and the end of the Mesozoic. And what we've got going on in the world is that there's a supercontinent, Pangea, that is breaking up. So all the continental masses are together, most of them, and they break up. The Atlantic Ocean starts opening up, right? North and south and north. And as it opens up, it pushes the North American plate into the Pacific Ocean floor, the Farallon plate, and that heavier ocean floor subducts underneath, generates areas of magma like the Bitterroot granite outside of the Bitterroot Valley, right? In central Idaho. And it also compressed the crust and it made a big, thick pile of sedimentary rocks that are all folded and faulted. Here's an example of one from the Burma Road north of town, on the Big Hole. This is between Glen and Twin Bridges on the dirt road. And you've got old rock here, PP, that's the Phosphorus Formation. On young rocks, Cretaceous Kootenai Formation here. And there's a fault there that has pushed the old rocks up over the young rocks. And that's from this compression that occurred during the Mesozoic. So it created this big, thick pile as these two plates are pushing against one another. Got it? Everybody good? All right. A welt, if you will. And no Missouri. Okay. Instead, this big interior seaway connecting at the Arctic with the Gulf of Mexico. All right. As we head into what we call the Eocene, say 50 or so, 53 million years ago, give or take. This compression is starting to subside because in Washington State and Oregon, terrains are being accreted on to the western edge of North America, and the subduction zone is jumping further and further and further back to the west, so that the bulldozer is backing off the pile. Make sense? Everybody good? And you got this thick pile of welted crust, the folded thrust belt, we call it. And that's me.
Which side is the bulldozer?
Somebody's saying that BS. That guy is full of BS.
What side is the bulldozer? Is the bulldozer coming from east to west?
So the bulldozer,
Against that subduction zone?
it's so the bulldozer, the Farallon plate is subducting off to the west.
Yeah.
And the North American plate is off to the east, pushing into it.
So which side is the bulldozer backing off?
This is the bulldozer. So what's happening is there's non-subductibles terrains out here, and they're coming along, and boom, they get accreted on. The subduction zone jumps to the west.
Oh, it goes west. Okay.
Does that help?
Yeah.
Okay. So by Eocene time, you've backed way off of this point of contact between the two plates, which started around Spokane, Washington, in Cretaceous time. Everybody good? All right. So the bulldozer's backing away, and this pile of folded and thrusted rocks in Montana and western Montana are going to fall apart. So when you back off, the plate and the welt of material starts to extend. And because it's brittle, that extension creates basins and ranges as it breaks up the crust. Y'all with me? Okay. Now, in the very earliest phases of this, the faults were very low angle, which is not represented well by that diagram, but that iris diagram is the best one I've got to illustrate extension and basin and range. But these low angle faults create rising domes of metamorphic rocks, and all the overlying rocks slide off. And so we have things like the Bitterroot Metamorphic Core Complex over in westernmost Montana, and the Anaconda Metamorphic Core Complex, which is north of us up west of the Deer Lodge Valley. Okay, it's well exposed in Mill Creek out of Anaconda, and so this is the beginning of extension around 50 million years ago, something like that. And we think that it's related to reduction in compressional stress with crustal relaxation. So the bulldozer's backing off, okay, and the pile is falling apart, and it's creating extension in western Montana. Everybody good? All right. And we see some other evidence for this. Not only do we see evidence of formation of basin range topography starting at this time, valleys like the Bitterroot, the Big Hole, the Deer Lodge, all have sediments that go back to about 53 million years ago in them, so that we know that they were creating holes by that time. Everybody good? That we're filling up with those sediments. But we also know that they're interbedded with volcanic rocks. And when we look carefully at those volcanic rocks, we see a transition from the kinds of volcanic rocks that form where plates collide, what we call felsic volcanic rocks, to those that form when plates pull apart, what are called mafic igneous rocks, volcanic rocks, the dark ones, okay? Basalt. So we go from granitic-like rocks to basaltic-like rocks, rhyolite, if you will, to basalt. Everybody good? There's this transition that goes on through the early part of the Cenozoic. What it indicates is the transition from compression, which the previous slide shows, of the plates subducting, to now extension, because the subduction is backing off and it's falling apart and extending. Okay, so Block Mountain, many of you locally know about, north of the Big Hole. That's a basalt flow with a 46 million year old date on it. And it's part of this transition into mafic extensional volcanism. We're pulling apart. There's no question about it. By Eocene time, 53 to 40 million years ago, we're pulling apart. There's still no upper Missouri River drainage as we see it on that map that I showed you at the beginning. All right. So between 40 and 23 million years, that extension continues in a very well-defined zone of extension develops in the western part of the state. It's very correlative with what was the old area of compression and stacked rock, what we call the severe fold and thrust belt. So this is good evidence that it's this collapse of the big gigantic welt of crust that had formed during Mesozoic compression that is causing this extension. At this time, they're correlative in space, if you will. Make sense? So the pile that has been generated by the colliding plates is falling apart, and they overlap one another as a result. All right, it created basins, and those are shown in yellow. Big basin over here called the Renova Basin to the east. This is on rock that didn't form this big thick pile. Instead, those are areas where basement blocks got popped up like the Beartooths over by Red Lodge. Okay, what we call the laramide uplifts. Those reacted differently to this extension that occurred, and they created there was a big large basin in that area. All right, so let's focus on these basins and ranges within the zone of extension. All right, so they're forming topography that looks like this. And so you're getting debris flows, alluvial fans that are coming off the ranges and going down into the valleys. And you're having streams deposit sediment in the valleys. And there are lakes. And the lakes are likely internally drained. What does that mean?
They have no outlet.
They don't have an outlet. How do I know that?
No flow paths out of the lakes.
What's that?
No flow paths out of the lakes.
Say that one more time.
The flow paths, there's no flow path.
Okay, there's no flow path out of the lakes.
Evaporate or
Evaporites. So we've got evaporite deposits that show that the lake dried up. Okay, lakes dried up. Okay, and you see these deposits all over in southwest Montana, and they're loaded with fossils of insects, some fossil fish, and a wonderful fossil flora. Okay, yeah, they're super cool.
gypsum.
Yep, there's gypsum deposits. There's there are other salts as well, and they've been mapped to the point, and sections have been measured to the point where we can actually reconstruct these old lakes and how they dried up. So we can be pretty confident they were internally drained. So what's the point of that? No Missouri River drainage yet. Okay, we got basins and ranges, but they're coming in and they're internally draining, drying up, making salts, and they're not exiting into a big fluvial system, the Missouri River. Everybody good? Okay, so we're now to 23 million years ago, and we still don't have a Missouri River. Now remember, I know it was when God was a child, but when I started, people looked at the topography of southwest Montana and said, it's been like that for 50 million years, since the Eocene. So what I'm telling you is developed in the last 30, 40 years of research. It's a completely different view. Okay. So finally, the upper Missouri River starts 17 million years ago. Why? The Yellowstone hotspot rears its ugly head down in the three corners where Oregon, Idaho, and Nevada meet. It's called the McDermott Volcanic Field. And it came out, and it's a gigantic source of heat. So the crust around it is going to do what? It's going to bulge up. You're going to get a thermal bulge around it. That is true still today around Yellowstone, right? It has a thermal bulge around it. That's why the Beartooth Mountains are sitting at 10,000 feet and change. Well, 12,000, right? At its highest point. That's why the Absarokas of Wyoming are at 10,000 feet plus. Everybody with me? Okay, it's a big uplifted terrain around the hotspot. So when the hotspot came out, it had a radial pattern of thermal bulging around it, and everything drained off of it or around it. So here's the Colorado River going around it. Here's the Columbia going around it. Here's the Missouri going off of it. Guys with me? All right.
And the faults are northeast.
They're northeast. All right. So when the dome rises, it's thermally expanding up brittle, rigid crust. So it doesn't pull like taffy. What happens to it? It breaks, it shatters, and it shatters into basins and ranges. So the Missouri River followed basins, what we call grabens. Structural geologists call it grabens. It followed basins, valleys, and it went into the Hudson River, or into Hudson Bay. How do we know that? Anybody know?
Wasn't it zeolites?
Johnny, you know.
Yeah, I think at the presentation from the professor Sears or whatever.
What does he know?
Yeah, well, I thought it was kind of interesting, and I think it had to do with zeolites that they were, some sort of mineral that they tracked in.
Zircons.
Zircon, I knew it was a Z.
Yeah, there's traceable materials, right? You can find the you can find the deposits, the deltaic deposits from this time period exist, and they've been cored, and so we know that it was going into Hudson's Bay. So I don't want to talk about that end of the Missouri. We just want to go. We got enough to digest here just to stick with headwaters. All right. So the thermal bulging occurs. It cracks the crust radially around that dome, and it creates northeast trending basins and ranges in southwest Montana. Everybody good?
Yeah, but how did that compare with the basin and ranges? That's northeast from the hot spots at this later time. And the earlier ones, the basins
They
and
were
ranges
pretty north.
Going north-south.
Yeah.
Does that explain what you're showing us on that first picture then? Sort of?
Yep.
Okay.
It's so overprinted that the earliest phases are so overprinted as to be somewhat lost.
But presumably this hot spot cut across the earlier north-south, the more north-south trending ones. Is that
Correct.
because it came afterwards, right?
Correct.
Okay.
Yep. And it made them lost to some degree. You can find little pieces of them, but.
Yeah.
Okay.
Well, I have a question.
Yeah.
Sorry to interrupt.
No.
This radial pattern.
Yeah.
Are the traces of the normal faults always pointing toward the center of the hotspot?
More or less.
So if we were to go to, say, the west
Yeah.
of the hotspot,
Yeah.
we would have extension north-south.
Yeah. And you can see them, like see the orientation of the faults. So these are mapped faults. These aren't made up, right? And so these are mapped normal faults, all of which are 17 million years old. So there's a radial pattern of normal faulting all the way around the thermal dome. Yeah. Of course, the Basin Range is happening at the same time in Nevada. And so it's hard to parse out how much of this is Yellowstone hotspot and how much of it is, Basin and Range, or whether you even need to parse it out because Yellowstone is in the Basin and Range. So they're one and the same, right? It's a radially domed area within the Basin and Range. So there was a question.
Yeah, just
Sam?
on that, you have the rivers that were going like around it, but
Yeah.
you said that the Missouri was coming off of it.
Yes. So
Can you pull that out?
so here's the Missouri River coming off, going to the
So
northeast.
Why is the Missouri River coming off of it and not going around it?
Because it had there were cracks in the crust that created downdrops that caught water off the dome and it flowed out.
Okay.
Great question.
And you get the Yellowstone ice cap at this point too.
No, way later.
Way later.
Yeah,
Okay.
has nothing to do with any of that.
So what was the original source of the water in that situation?
Okay, so it's drainage off the thermal bulge.
Okay. I get the drainage pattern. What was the source of the water?
Well, it's raining on that thermal bulge.
Raining on it.
Okay. We're gonna get to major sources of water here in a minute. Okay, but yeah, it's a hydrological high, right? And so it's capturing moisture and it's draining off that to the northeast. Okay.
I'll wait and hear your story.
Okay. Just like Yellowstone today, right? Yellowstone today is a thermally expanded up area that has a much higher precipitation rate than the areas around it. Right? So that moisture ramps up over the bulge, is wrung out as it lifts, and you get lots of moisture over the top of the bulge. It's got to run off somehow. And if it's a bowl that it's running off of, it's going to run off in every direction off of it. Johnny?
I hate to do this, but I'm so curious about this. So
That's
do you
okay.
see the same kind of patterns in earlier supervolcano systems, like the Indian caldera in the Nevada, Utah border?
Yeah, they're not my expertise, but yes.
Yeah, interesting.
Okay, so to give you some context for those that know the local area, here it is. I'm standing on the, yes, I am standing because I took the picture on the top of Timber Hill, which is out east of town on the Sweetwater Road. And that's the track of the Missouri River 16 million years ago. And it's forming mazes because there's a basalt called the Timber Hill basalt that's capped and protected underneath it deposits of sediments. Whoops. I knew that would happen. Deposits of sediments that were deposited by that river from 17 to 4.5 million years ago. In this case, 17 to 6, because we have a very good date on this basalt of 6 million years. And I brought samples. So there's the Timber Hill basalt. It came from Idaho. It came from Idaho. Keep that in mind.
A lot of things around here came from Idaho.
60 miles.
All right. And there's all kinds of evidence that the flow is in this direction to the northeast in the sedimentary rocks. I had a student did a senior thesis project. She had 35 measured sections and did all these paleo flow analyses to track the direction that the river was flowing and made a map and showed that the river flow is to the northeast off the thermal bulge, right? Which was to the southwest. To the northeast. Everybody good? That's the beginning of the Missouri River. It drained off the Yellowstone thermal bulge, which cracked the crust, made valleys. The water came off of that surface, went into the valleys, and flowed to Hudson Bay. Okay? And it left behind evidence of itself. which is now preserved in mountains. All right, it's called the 6 Mile Creek Formation, and it's been my life for 30 years. I probably know it better than I know much of anything. I don't know much. So what we got is that older Renova Formation with the internally drained lakes, the nice leaf fossils. It gets eroded into, it gets tilted into these valleys that formed 17 million years ago. It gets eroded and it gets buried by these new deposits, what we call the 6 Mile Creek Formation. And there's 3 distinct members: the Sweetwater, Anderson Ranch, and Big Hole. The Sweetwater is made up of angular rock debris. Those are hand lenses if you want to look closely that are going around. Angular rock debris that were alluvial fans that came off of the adjacent mountains and came down into the valleys. Just like the alluvial fans coming off the Blacktail today, coming into the Blacktail Valley. Everybody with me? Okay. They're mostly angular and they're all locally derived. So you can find the sources of these rocks. They are nearby. Okay. Those are overlain by the Anderson Ranch and interbedded with. These things are temporarily, changing from Sweetwater to this, but they are also interleaved with one another. Okay. So they're not distinct. That there's a line and then you go to this. They interleave. All right. The Anderson Ranch is made up of ash. And it is about as spectacular a deposit that I've ever seen in my entire career. As you'll see in a minute, this thing are stream deposited ashes with a little bit of sand and some big chunks of older ash that was stream deposited within it. And the weirdest sedimentary structures you've ever seen in your life. Okay? What the hell is it? Hold on. We'll get to it in a minute. But what's our nearby source of a lot of ash? Yellowstone hotspot. So that ought to be where we should be thinking it's coming from. And we know that we got plumbing system going back to the hotspot because the Missouri is attached to the hotspot. It's coming off of it. Everybody good? All right. Interleaved with that and sitting on top of it, becoming dominant at the very end of this deposit, are gravels that we call the Big Hole River gravel member of the 6 Mile Creek Formation. And it contains exotic rock fragments, meaning they ain't from around here. Okay, these came from Idaho. We can actually trace the cobbles to their sources in Idaho. There's one black chert, which you can see in there. It's called the Milligan chert. And it's a very distinctive chert with white veins in it. And it came from a source in Idaho. It doesn't exist in Montana. It had to come from Idaho. All right? And it doesn't really matter because the ash had to come from Idaho because that's the source, Yellowstone, which is in Idaho at the time. All right. Y'all with me? Okay. On those hand lenses, put it right against your eye, bring that rock in till it's in focus. Okay. All right. So what do we see in terms of the environments that are recorded? So again, the Sweetwater Creek, the oldest of these members, are alluvial fan deposits from the local ranges. So the hot spot emerges 17 million years ago. It domes up the topography around it and creates radial drainages off of it, one of them being the Missouri River drainage. That creates basins and ranges as well. But so if we create basins and ranges, the ranges are going to have locally derived streams coming off of them going into that valley, right? Alluvial fans. And you get angular deposits of locally derived rocks. So here's a local volcanic rock in one of these deposits of alluvial fans of the Sweetwater Creek member. Okay? We can source that rock to its origin literally 3 miles away from this deposit. And we can be absolutely certain it came from there. You understand? So these are local, and they reflect the forming basin and range topography around the thermal bulge. All right? Then in comes the ash. And the ash is unbelievable. Look at this. That's a human being for scale. We call this one you bet your ash. They are over 100 feet thick in places, these ashes. And they did not fall from the sky. Not all ash falls from the sky. It was transported by streams. And there's nothing else in these deposits other than the ash deposited by the streams. And they have weird, bizarre sedimentary structures that show us that the flow was viscous. We call them lahars, volcanic lahars. And these are the weirdest volcanic lahars I've ever seen. They are just all ash. Fragments of ash in ash. There's a little bit of grains of sand, that's about it. Every once in a while you can find a stray weird thing, but it's mostly ash. All right. And in this case, it's not even sitting on the channel that it went down. See this peach colored unit that it's down at the bottom? That's a paleosoil. That's the floodplain. It came down this valley, it went down the channel, and it went out the channel and filled the whole valley wall to wall with ash. We've mapped it. We know that it did that. We've mapped it. Okay, this is up in the Sweetwater, the Ruby area, east of town. All right, and then the gravel coming in has these cobbles from Idaho, and they just add to the story that there's drainage coming off the Snake River Plain. And one of the things that we've learned about these cobbles is that we can trace them to the various hotspot calderas as they formed. Okay, so what's going on? Well, the plate of North America is moving to the southwest, and the hotspot is stationary. So as the plate moves to the southwest, it's like putting your hand over a burning candle. It's leaving a trace of itself through the plate. Y'all with me? Those are a series of calderas starting down here in Nevada, going to the northeast, and they're covered over by basalt, which is the last thing that comes out when these calderas erupt, and they get covered over like a scab by basalt. And that's the Snake River Plain. But in places we can see underneath the basalt of the Snake River Plain, and we can see the old calderas and their deposits. Y'all with me? And they've been mapped. The Twin Falls caldera, the Peekaboo or Picabo, however you like to pronounce it, caldera, the Heisey caldera, and then of course Yellowstone volcanic field. And they are getting younger. Whoops. They're getting younger that way. Right? 12 and a half, 10, 6, 2. Got it? All right. We ought to be able to track that in the cobbles. Right? And the ash. So we dated the ashes. There's a bunch of them. And the ashes from bottom to top, right, track to these various calderas. So this caldera was active, ash went in, went down the Ruby Graben, this ancestral flow path of the Missouri River. Then the plate moved. This caldera was active, domed up. Sediments, including ashes and cobbles, went into the river from that source. Then the Heisey went up, and ash and cobbles went in from that source, and a basalt flow, shown in red, the Timber Hill basalt. Y'all with me? We can track the movement of the hot spot in the sedimentary pile that was deposited in the ancestral Missouri River, which now sits in the mountains. You guys with me? This is cool. This is the coolest thing ever in my book. I mean, I sat on a ridge with Jim, and he unfolded the whole story for me before he even had the data. I went out and got the data, and showed that it was right. But no creative thinking going on in this brain. I came out of Jim. But I was blown away. And then in cross-sectional view, you can see these are interfingering. So orange is the Sweetwater Creek, remember, and the yellow, the white is the ash, and the yellow is the gravel, and the black line is the basalt. You can see they're interfingering, interleaved with one another inside view. So this is a general trend towards cobbles to the top. But they're overall interbedded with one another as well.
Are all these ash flows, are they all siliceous, or are some of them calcareous or calcareous members?
They are all siliceous. They're all, you guys have it. It's going around. The ash is going around. Take a look at it with the hand lens. You can see the little needles of glass. Okay. That's not easy to transport a little needle of glass from Idaho into Montana and not have it be broken. Yet a lot of them are not broken. What does that tell you about the flow?
It was massive enough to be insulated.
It was viscous. It was viscous. These grains weren't popping down the stream. They were flowing like a slug. You with me? Okay. And just inundating the valleys that they went down, going across the floodplains and covering the floodplains in tens of feet, up to 100 feet of ash. That was a bad day. If you were a myohippus, nipping the grasses, it's like, what's that? Boom. Wow. And we don't find them preserved, which is not at all unusual to me because it's very silicious, it's very porous as a result. So there's a lot of water flow, and that water tends to be acidic. So what happens to bone? Calcium phosphate dissolves away. So the bones are not that plentiful in these lahars. You'd think they might be, but they're not. Wrong geochemistry. There it is. So there's my daughter sitting inside of one of these events. Look at the size of this thing. This is out the East Fork of the Blacktail. I hesitate to even say that because it's got to be one of the most special places in all of Montana, and it's so easily ruined.
Is this the high sea that's you're seeing here?
That one? That's You Bet Your Ash. That's Twin Falls.
The source from the high sea.
10 million years.
Okay. 10.
It's the big kahuna. Yeah. There's two of them in there. The Twin Falls is really big, and the Peekaboo.
Okay.
All right. So this thing came in as pulses. I've been working on the details of the tephras because they really these ashes because they're fascinating. And what we can see is that they came in pulses, but they came in pulses probably over days to weeks, not years, likely. Why? Because at the very top, there's soil development on them, but not interiorly. There's no soil development interiorly, only at the top. And what you see, look at that. That's a root of a grass. A root cast. It's a fossil root. Outlined by calcite. And the grass is gone. The root is gone. But that root cast, what's called rhizolith, is preserved. They're all over the place. Can't go in the field, I brought it to you. Those are rhizoliths. You can see them all over that surface. That's the soil at the top of the ash. Everybody good? All right. And then the gravels, they get bigger and bigger and bigger as you go up in the 6 Mile Creek Formation. So here I'm at the top of the deposit. And look at the size here. Okay, these things are this big around. Whereas the piece I passed around, they were this big around, which was from down low. Why are the cobbles getting so much larger as you go up, 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 up in the 6 Mile Creek Formation?
That should be a lot of water.
Okay, what's going to allow transport of a larger cobble? Higher energy. And what controls whether there's higher energy or not?
Slope.
Okay, gradient, right? Gradient might control that. So if here's our northeast trending Missouri River, and the hot spot is coming towards it, right? Because the plate's moving this way. And the hot spot's coming towards it. What's it doing? It's getting, as it gets closer and closer, the gradient increases because that thermal bulge is getting closer and closer and closer to our area. And it's causing the whole landscape to tilt like this. You understand? That means that the cobbles are bigger because the gradient is higher. We've really well documented this. We've looked at the changes in cobble size from the bottom of the 6 Mile to the top, and they go from pea gravels to big boulders from bottom to top. It's reflecting the whole northwestern part of the whole southwestern part of Montana being tilted up from the oncoming hotspot. That's super cool. Okay. Everybody good?
Great question, sorry. So that's in
right.
contact with the 6 Mile Creek is the change in those cobbles? So it was like that?
No,
fast?
so there's cobbles throughout the whole 6 Mile Creek,
Uh-huh.
and there's ash throughout the whole 6 Mile Creek, and there's the debris flows from the local sources all the way through the 6 Mile Creek. The cobbles down at the bottom of the 6 Mile Creek, furthest away from the hot spot, right, when it was down in Idaho, Nevada, and Oregon at its outbreak point, are pea-sized cobbles. By the time you get to the youngest deposits, where it was really close to the Dillon area, the cobbles are this big. And it reflects the progressing tilting. And there's actually a curve that I had students work on. They measured all these cobbles, and then they put together a curve that shows the increasing size in the cobbles as the hotspot got closer and closer and closer. Okay, there's a gradient.
Do we have some more water at that time too?
Well, okay, so before I move on, so this is going to your question about water. So these outpourings of river deposited ashes that occur in a matter of days to weeks, months max, maybe, I don't know for sure, not years, are perplexing, right? Where do you get all that water? The ash I can derive, okay? The Yellowstone hotspot is the biggest explosive volcanic center on Earth. So when it goes, it's generating a crap ton of ash. No problem there. Take a look at Yellowstone today. What is in the Yellowstone area that is a source of water?
What big lake?
There is a big lake. Why is there a big lake there? It's a caldera. What's a caldera? It's a hole. Holes filled with water. These past calderas of the Yellowstone hotspot tract filled with water made lakes. A new caldera would erupt. It would bust the wall of the old caldera. The lake water would spill out with all that ash that formed from that caldera eruption. And boom, you got yourself, you bet your ash. A big lahar from a catastrophic outburst of water from the lakes inside the caldera that ruptured during an eruption that created the ash. We're working on that. I say it with great certainty, but we're working on it. That's what I see right now. I have to document it. Okay.
Mount St. Helens.
Yeah. Yeah. In case of Mount St. Helens, a composite volcano, a flowing cloud of hot gas ash and rock fragments hit the lake and pushed a bunch of lake water out, right?
Same stuff.
Same stuff, right? In this case, I envision that the caldera walls rupture and it drains the lake. But because caldera eruptions are a little different than composite volcanic eruptions. All right, let's finish this guy off. So 4.5 million years ago, Northwest trending basins and ranges form all of a sudden. Boom. Just all of a sudden. Why does this happen? Well, the plate, so here are the calderas, right? The hot spot's always been here. The plate's been moving this way, a couple of centimeters per year, about the rate at which your fingernail grows, over that stationary spot. All right. As the hot spot got closer and closer and closer and closer and closer to southwest Montana, cobbles got bigger, the ash coming in got more. You guys with me? And then all of a sudden, boom, it all stops. It stops at 4.5 million years. We have it well documented. What happened? Well, the hot spot reached about right in here. Well, southwest Montana, the area we're working is back here. Whoops.
Tap the arrow on the screen.
I know. It's touchy. It's back here. So what happens is you've got this crust that is held up around the thermal bulge. And when the thermal bulge moves away, that crust falls down. And it is brittle. So it breaks into basins and ranges. And so a whole new set of basin and ranges formed once the hot spot got past the Dillon area. And they were northwest trending. Y'all with me? Okay, this is happening right now. Jackson Hole has dropped because the hot spot has moved away from it. It's not holding it up anymore, and it's falling. We are making valleys. We're not making ranges. The ranges were there around the hot spot. It's the valleys that are dropping. Y'all with me? The Centennial on the north side. All right. So that crust held up by the hotspot dome collapse. Northwest trending basin and ranges form. The rivers then are diverted into those northwest trending valleys. I like to envision that one day flow down the northeast trending Missouri River system. It was going down this drainage system, and boom, up popped a 25-foot fault scarp, just like Quake Lake in 1959. And the river all of a sudden turned into the new valley that had just been created. And there were fish flopping around on the dry riverbed that got cut off. The old northeast trending flow got cut off. And it went into a northwest trending valley that had just formed instantly. And we know it can happen because we saw it in 1959. Okay. In a few places, the rivers cut canyons out of rising mountains. So these northwest trending rising mountains like the Blacktail, the Beaverhead cut a canyon right across it. There it is. There's the Tendoy Range. The flow of the ancestral Missouri River used to go back to Idaho right through that range. That range has popped up in the last 4.5 million years, cutting off the old northeast flow of the ancestral Missouri River system. You got it? It's scary. That range is scary. All right. And we can be absolutely certain that I'm not just making this up, because here it is at Timber Hill. In cross-sectional view, there's the Timber Hill basalt flow. There it is again. Now, that was either one heck of a big waterfall or lava fall of basalt, which it was not, or that's the old stream drainage going from left to right, and it's been cut by this fault, which is a northwest trending fault called the Sweetwater Fault. It uplifts the Sweetwater Range, down drops the Sweetwater Valley, and it's cut all the old deposits of the ancestral Missouri River, the 6 Mile Creek Formation, by that fault. You guys with me? Let's look at it. So there's the gold. Here's the old path. There's the ancestral Missouri drainage. Okay? Going from Idaho into Montana, flowing to the northeast. In blue is the 4.5 million year old valleys to the present, the Red Rock, the Blacktail, the Sweetwater, which flows that way, the Ruby. You guys got it? So in places, the ancestral flow path remains. So from Clark Canyon Reservoir, across the canyon of the Beaverhead, across the Blacktail Deer Range, and following the Beaverhead River up through the Jefferson River, that path is held. This path, on the other hand, did not hold. Okay, so in here are old deposits from the ancestral Missouri. They're in here, they're in here, they're in here, exposed to the mountains.
So is that the Wade Cliff and Hidden and all of the ones there, or is that?
No, unrelated. Okay, so here it is on a map from Roadside Geology. Here are the old northeast trending faults shown in red that formed the grobens that the ancestral Missouri River flowed down. And here's the active ones that are cutting it, that formed because Yellowstone passed and the crust fell apart. You guys with me?
Mm-hmm.
So here I am standing on it, and here's that beautiful ash from one of the eruptions, and here's some of those gravels with the far traveled cobbles in them. And you're looking out there, and there's the Blacktail Deer Range. That should be the flow path of the ancestral Missouri River. It's not. The flow path is the east fork of the Blacktail Deer Creek, which goes into the northwest trending Blacktail Deer Creek, or Blacktail Creek, whatever you want to call it. All right. So the active earthquakes are on these northwest trending normal faults. And we know what happens because stress builds up and then boom, blocks drop down, valley building, right? And we know from Quake Lake that it's mostly valley building because we had offsets on scarps of 27 feet and about 3 feet was up and the rest was down. So we're valley building. And as it does, it leaves ruptures in the ground. This is the fault scarp from the Quake Lake earthquake in 1959. There's a human being for scale. If you can't see it, that person's this big. Whoops. That's a big, whoops. We're almost done. That's a big offset. Okay. Then in 2005, we, those who have been around Dillon long enough, know that we had a pretty good shaker of our own. And it occurred along a fault that is uplifting and tilting back the Pioneer Mountains along a northwest trending normal fault, an active fault. We didn't know it was there until it ruptured in 2005. It dips into the ground and its epicenter is out here in the middle of the valley. or broke 3 miles below the ground surface. It's dropping this valley and it's raising this range. And it's active and it's northwest trending. All the active faults are northwest trending. Every one of them. None of the northeasts are active. They might have a little movement on them, right? Because they're areas of weakness and you're adjusting the crust and it might move a little bit. The active movement is on the northwest trending extensional system. Okay. The earthquake in 2005 created what I consider to be one of the best pictures I've ever had. The Jenga chimney. This is my neighbor. It sat like this for years. It's only in Dillon. Right? It's like, good enough. That's good enough. Okay. So the positive in all this is we got hot springs and they come up along these active faults. So every place you see a hot springs out in southwest Montana, that's coming up along a northwest trending normal fault.
Yep.
Every one of them.
Yep.
Okay. I don't care if it's that little hot area out there by Beaverhead Rock, or whether it's Elkhorn Hot Springs or Jackson Hot Springs, every one of them is on a northwest trending normal fault. Why? That's the active movement in the rock to depth. You got to get down deep to get hot water, and it's got to get back up. So it's got to have a porous and permeable rock to get up, to get out. That's the active fault movement planes. That's how it migrates back out. So it flows down in, hits the fault, comes out, boom, Jackson Hot Springs. Got it?
Mm-hmm.
All right. Downside is in Butte, Montana, Our Lady sitting atop the East Ridge is rising into the heavens while Butte is dropping into the pits of hell along an active normal fault. And it is a town with historic tall brick buildings underlain by holes.
Yeah.
And in the flats is a former lake. And when and if you rupture a 7.5 magnitude earthquake like happened to Quake Lake in 1959 on the East Ridge, what's called the Continental Fault, it's not going to be a good day in Butte, Montana. Because I would venture to guess there's a high probability that the Yankee Doodle tailings pile uncorks, hits the pit, creates a tsunami wave, and takes a good chunk of uptown off the face of the earth.
I don't know how many people have seen it up close, but the first time I saw it in 71, taking samples, it gave me the creeps.
Yeah.
From eye level, it looks huge.
This is just recorded, so you and I are now in trouble.
And I was an employee.
I will say, this is for dramatic effect. Where's my camera? For dramatic effect. Okay, may never happen in anyone's lifetime. Likely won't. Probabilities are low.
The offset on the Continental is what,
Don't-
300 plus feet?
Yeah, easy, right? So, okay, so with that, I will entertain any additional questions. Thank you very much.
Thank you.
Sorry to go over.
That was fun.
It's a big river.
It was fun.
Questions? Okay, well, I'm happy to answer them. I'll stick around. If, yeah, yeah.
So when you get into the big changes on the Jefferson and the goal that you talked about,
Yeah.
really changed that.
Yeah, let's go back to that.
Was that immediate thing then?
Yeah, let's go back. Oh, I can't, I gotta go back to this. Okay. All right. So these are weird. All right. And what we think is going on there is they are old remnant stream paths that developed during Renova time. So going back to those deposits from the Eocene and what we call the Oligocene epochs.
Those don't have much to do.
Now, what's happened is that the ground is uplifted under those old pathways and they've got dissected canyons. And so the northern tip of the Pioneers has come up along the northwest trending normal fault, and that river path has been there for a long time, and it's just dissected down through it. What we do know about the Big Hole is the Big Hole flowed out of the Big Hole and into the Deer Lodge. And it got cut off because of a northwest trending normal fault that uplifted a range that blocked it.
So it's kind of a fault line, old uplift at river cut.
Yeah. So these, you can't underestimate how important the northwest trending normal faulting is today. It is, it's dramatically, changing the flow paths. But there's remnants, right? So we can see the deposits from the old northeast flow, and even in places we can see the old northeast flow, right? Like the Beaverhead Jefferson system. And we can see it cuts across the Blacktail Deer Range and makes a canyon. So that range had to have uplifted into the river. The river had that flow path from 17 to 4.5. From 4.5 to the present, it got dissected down through making a canyon. Okay, that didn't happen for this one down here. That was going down the Ruby, the old Ruby drainage. Where is that? That's right here. The old Ruby drainage. That one didn't. That one got cut off and went into the Red Rock. It didn't persist. Why? Just didn't persist. Probably a big rupture of the fault immediately caused the diversion of water. Done. Right? Versus a slow uprising of the rock underneath, which is what probably happened here across the Blacktail.
Could I see the figure with the Columbia River running around the hotspot and then the Missouri coming off of it? I couldn't see it back there.
Okay.
Okay.